scene 1. Okay, that's the image I'm at. Are you at that image?
Mm-hmm.
Okay. All right. So at what point would you say the curvature visually can be ascertained?
Right at the very beginning, man. Just hold a straight edge up to it. You can see it.
So you're telling me that all the way to the very left of the image where the causeway stops, you're saying that that's where the curvature begins? Visually, like you could say, I can see curve there. Because I don't.
No, dude. Okay. What you do is you take a straight edge, like a piece of paper, and you put it on the bridge. You put it on the bridge on one
I'm
corner.
asking you. No. I'm being very specific and
I've already answered you very specifically from the right side of the image.
Visually,
right from the right side of the image, I can start seeing the curvature. Yes, but you can't just say which pixel do you start seeing curvature. That doesn't make sense.
I didn't say which pixel.
Right. Okay. So you have to talk about a range, right? So that's why I'm talking about holding a flat edge against the actual bridge there. If you hold a flat edge against that bridge, you can see that the curvature starts very early. You can see it yourself. Like you can't avoid hitting the bottom of the bridge very, very early on. Like
so how far away? So how far away are you from that box that's right there? That last one by the Y.
Again, this is exactly what I was saying earlier. I have to assume that's about a mile, just based on memory right now. I'd have to go look it up and figure it out, the exact distance.
Don't those boxes, aren't they numbered? Right? Wouldn't we be able to look up which one it was and see where it is on the mile marker?
I'm sure the Causeway Commission has a number on it. And yeah, you could obviously you'd be able to tell which mile marker it's close to based on Google Maps.
All right. So, in your opinion, is there refraction happening in this photo?
There's always refraction happening in the atmosphere.
Okay, so yeah, but if I were to show this photo to your team and say that it was my photo, I'd get balled out because there's distortion and refraction. They would say that this.
What refraction? What are you talking about?
Okay, so the box.
This is why the model's important, you know.
Okay, so when you asked me a question and I started to talk, you then kept talking. Are you finished?
No, let me continue. So this is why I don't know why you don't want to look at the model, but this is why the model is important, because it shows you what you should expect to see, and then you see the actual observation. And so, what refraction are we talking about?
So okay, right, great. So the box that's closest to us near the Y is a clearer image than the one that's even right in front of it, farther away. That one has fuzzy edges, or what I would be accused of taking is a blurry image. It's a blurry image.
No, I mean things that are further away are blurrier, right? I mean,
I don't have a problem with that. I'm telling you that if I had this picture and I was trying to present it to your team, excuse me?
That's false. I mean, you can't.
What's false? Because since I wasn't
get clearer pictures. I don't have a team, so that's false.
Since I wasn't finished talking. Since I wasn't finished talking,
don't give a fuck, dude. Don't give a fuck. That's how conversations work, bro. That's how conversations work, man.
Whenever you say something false,
I will correct you.
What did I say was false?
My team. I don't have a team. What the fuck are you talking about?
Okay, those who are on the side of the globe, your side, Ruhif, Rumpus, people like that, are they not on your team?
No.
They're not on your side?
No, I don't really consider it a side, dude. I have observations. That's what I stand behind. My observations.
Okay. All I'm trying to point out is that you have refraction in your photograph. Okay? And that refraction distorts the image that we are looking at. So
can I respond to
that? I was sure.
Yeah. All observations, especially long distance observations, are going to have refraction affecting that image. But what's the point? What is your point? That the
Well, see, that's
the
what happened when
refraction
I
the
was saying
refraction the
so.
refraction affecting the
When I
image
was saying
is something that we need
so,
to
and you
minimize.
right
We
when I was
need to
saying
minimize that as much
so,
as possible.
right when I
So
was saying
that's what we
so.
should do. Yeah.
Okay, so when I was saying so, I
I'm
was
just gonna
going to
ignore everything I said.
extrapolate, and you interrupted me, and then said that I needed to explain. But that's what I was going to do when I said so.
All right,
Because I was
stop telling
going
me
to
what
say,
you're going to do and do it.
so why don't you try not to interrupt my statements and let me
No, I'm
finish my
good.
statement?
No, I'm good. I'm going to do what I'm going to do, and you can go ahead and do. You can go ahead and explain what you want to explain. All right, go ahead.
I don't know that I can because sometimes you might interrupt me.
I do interrupt you when you're wrong. That's correct. When you make a blatantly obvious error, then I'm going to say something. I will do that.
Uh-huh.
See, I don't like the whole Gish Gallop thing, and that's what you're trying to do.
What's Gish Gallop mean? What is that?
That's when you say a bunch of things in line that I can't respond to any of them. So responding to one of them somehow gets that response applied to all of them, and that I don't play that game.
Huh. Interesting. Okay. All right. So what I'm going to do is just try to save this image, and I'll do some editing on it and try to get back to you in terms of what I think is going on here. But,
so also try and explain why the GPS coordinates and the
I don't
3D
give a shit about the
model
GPS or the 3D
Well, you
model.
should though. See, that shows
No,
your
I shouldn't.
closed-mindedness. Yeah, it does. You should, because what we've done is we've actually shown what the bridge should look like on a globe, and then we've actually measured it in reality and determined that those measurements actually map to the 3D model. The 3D measurements of reality map to the 3D model, which are not affected by refraction in any kind of way. And then my photograph also matches the 3D model and the GPS coordinates. And so what that should be a clear indicator to you is that this argument that you have about refraction being this magical thing that makes flat Earth.
I didn't use the word magic.
I'm using the word magic.
Well, I'm going to interrupt you because you're wrong.
Okay,
it's
good.
not magic.
Good. See, you see how that works? Good job. I like that you interrupted me whenever you thought I said something wrong. Yeah,
Thanks,
you're welcome.
Dad.
You're welcome. Good job, son. So the point is that it does look like exactly what the model looks like. And so it's a clear indication that these claims about refraction and about atmospheric disturbances are just wildly overblown. Like they just don't apply.
Are you telling me?
Photographs.
So are you telling me that if you overlaid your 3D rendering to the physical photograph,
that's
that
already been done, yeah.
it's a 1-to-1?
It's really, really close. If you actually look at the at Walter Bislin's website, he goes through a full series of these videos and models. These photographs and models. Like he flies through it for a bunch of different observations. So
okay,
yeah, I definitely suggest taking a look at that because it's definitely worth looking.
No, I'm just going to try to figure out whether or not your image here can overlay on top of it, and it's going to be a 1-to-1 correspondence.
Yeah, that's what I'm saying. It's already provided for you on this website.
No, I'm going to have to do it myself. I'm going to have to do it myself. I'm not going to be happy with looking at somebody else because I would rather try to understand these things myself. So
okay.
let me just try to understand. Yeah, whatever. So what I'm trying to understand is that the first 3D rendered image, which is on the right side of the causeway, right?
Okay.
What's that pink line represent?
It's eye level. It says it on there.
Oh, well, I can't see. It's too small. So I'm just looking at it this way. Okay, so it's eye level.
Eye level.
Okay. Okay, so then these images then on that one from the right side of the causeway, these weren't taken from the same elevation then, just to be specific.
It doesn't appear to it, right? I think the left side of the causeway is higher. Yeah.
Right. So we're not looking from the same angle.
Yeah, actually, the left side of the causeway I have taken some from the Marriott hotel's parking lot. You know how the Marriott hotel has a parking lot, like you can drive to the top of it.
Yeah, I've been there.
I have taken some photos from there, so it could have been from that vantage point. I actually don't remember. this particular photo.
Okay.
It's easy. I mean, if you actually want to know exact locations, it's easier to look at my videos. I put exact GPS coordinates and stuff like that on the videos.
Yeah. All right. Well, I do think that there's a glaring disparity in the physical photograph that I doubt is in the 3D rendering. So I'm just going to have to take a look at those and get back to you on that. So I'll do that.
Well, I mean, I'm looking at it right now. They look the same. But anyway,
that's fine. That's fine. I'm telling you that that's what I'm going to have to do. I'm going to have to get to a place, not on my phone, where I'm going to be able to compare these two images, because in the physical image, I see an absolutely physical depiction of refraction that I would, if you're not going to have that in the 3D rendering, then it's not a one-to-one correspondence. So I'm going to have to just look at those images and get back to you.
The 3D rendering does have that. There's refraction on these images built into the 3D rendering. If you want to go look at the actual website, you can see where you can actually tweak refraction, play around with it. You can turn a whole bunch of knobs, play around with it.
Yeah, well, I don't see I don't see those towers looking fuzzy and distorted the same way the physical image is, so that it's not a one-to-one correspondence.
Yeah, what are you talking about? Hold on a second. Are you saying that seeing conditions and turbulence in the atmosphere is what you're calling refraction? Those are two different things.
Okay, so the structure that is above the D in the bottom photograph, right?
Yeah.
That structure is blurry, correct?
I mean, it actually looks pretty sharp if you look at the rails. I don't know. Maybe blurry. You're talking about like it's not as clear as the one in the foreground. Like you can't see as much detail as the one in the foreground.
The one in the foreground is much more sharp than the second one.
Because you're looking through less atmosphere and it's closer.
Okay, but so now you agree that it's blurry.
I agree it's further away and it has less detail in it. Yeah.
Why does it have less detail?
Because it's further away and smaller.
No, it lost its sharpness. It's not as sharp as.
I don't know, bro. I'm looking at it right now and it looks pretty damn sharp.
So am I. Absolutely not.
Aren't you on your phone?
Yeah, I'm zooming in.
Okay. Well, I mean, whatever. I don't really know where you're going with it, but it's less sharp than the one in the foreground because it's further away. That would be my assessment. You're looking through more atmosphere.
So go to the third one that's right above the U and the N.
Right.
Is that
so it's a little bit more blurry, that one, yeah. I'll give you that.
Oh, so that one you're okay calling blurry.
Yeah, that one's starting to get a little bit further away and as it gets further and further away, it gets more and more blurry.
I agree. Is that refraction?
Probably not. It's probably more like atmospheric turbulence. Yeah.
You don't think that that's refraction?
No, refraction would actually pull the whole image up. When we're talking about standard refraction, you'd see.
Yeah, the standard refraction doesn't exist. So, okay. I see where we're at here. All right, yeah. Like I said,
standard refraction doesn't exist. That's hilarious.
It doesn't. It's a conventional way of speaking. I mean, Andrew Thomas Young.
It's a way of averaging the sight path, like the effects over the course of the entire sight path.
Yeah, it's a conventional way of speaking. It's a convention. It's not real.
Yeah, I understand. I understand exactly what it is, but it is the average of all the disturbances caused by refraction over that sight corridor. That's what standard refraction is supposed to be representing. So it's a best guess at what the effects are over the entire sight corridor. That's
so so what I hear you saying then is, in your opinion, the conditions of this day in this photograph are standard atmospheric conditions?
They were pretty close, probably. I generally try to minimize those scene conditions problems, but I do have observations where I just went out randomly, just at different times. Like when when I expected to see looming, when I expected to see sinking based on atmospheric conditions, I went out to try and capture those.
Oh, you know when you can go see sinking?
Yeah, I actually have a video on my site where I predicted it and then recorded it.
Oh, wow. Could you link that? Because I've been trying to figure out what conditions are right for sinking. So I'm curious, how did you determine that this was standard refraction?
I didn't. I tried to minimize for atmospheric refraction.
Oh, I thought you said that these are the conditions for standard refraction.
I said it's yeah, the conditions right. The conditions were right. When the surface temperature and the atmospheric temperature are the same, that's when you have the best viewing conditions and the best chance to minimize atmospheric conditions.
And when does looming happen?
I don't remember that one. I think that's when it's let me try and remember. It's always it's always a difference between the surface temperature. I can't remember exactly how they apply now. I'm trying to remember it in my head here.
Okay, so just for
it's when the surface temperature is so what'll happen is like say there's a cold front, right? And there's a cold front that just kind of sits over the area for a while and the water gets really cold. And then a heat front comes in. And when that heat front comes in, you'll have like a hot atmosphere sitting on top of cold water. And that's when you get some really wicked stuff going on. And then the same is true in the opposite direction. Whenever you have hot water with a cold front that comes in, cold snap comes in on top of hot water, the opposite will happen. So that's generally when you get those types of seeing conditions where you cause looming and sinking.
Yeah. So in my research, and I'm inviting you to correct me if I'm wrong, not right now, because I don't think that you know it immediately. I think that you're going to have to look it up, which is fine because I don't
have
know.
to kind of remember. I know when the water is colder, the air that's the looming condition. So when the water is cold and the atmosphere is hot, that's when you get the looming conditions. And then the sinking conditions is the reverse. It would be hot water and cold air. Yeah.
So Andrew Thomas Young is an emeritus professor, PhD astrophysicist at San Diego State University. I don't know if he's still alive. I had correspondence with him from 18 to 19 or so, and when COVID happened, we just lost touch. Okay, but he has done a tremendous amount of research. Rumpus is where I first heard from him because Rumpus would always appeal to Andrew Thomas Young. So I started looking up Andrew Thomas Young. Now, as I have looked into Andrew Thomas Young, it is my opinion, and I've tried to understand this stuff. It's my opinion that the conditions that are considered standard are actually the conditions for looming. Now, again, I'm inviting you to find something, send me a link that shows me that there's actually more specific information as to when looming actually happens. But
I mean, this is what I base my guesswork on whenever I tried to, because I actually live an hour away from the bridge, so I have to kind of plan my trips and try and be smart about it. And for a while, I was just driving out there randomly, and I said, okay, I got to stop doing that. And so what I started doing is trying to make predictions about what type of conditions I would see based on buoy temperatures, atmospheric temperatures, stuff like that. I would look at the weather, I would look at buoy temperatures, and then I would try and predict what time that buoy temperature and atmospheric temperature would cross. Like there's a graph for both of their temperatures. I try and predict when those temperatures would cross to get the best. These are the times when I was looking for the best seeing conditions. So there are other times where I went and I didn't really care about seeing conditions and just got whatever I got. But whenever I was trying to predict when I would see the best seeing conditions, that was my approach and that was my plan, and that worked. So that actually worked very well, and I was actually able to capture some like really sharp images on those days.
Have you ever compared images that you've captured when there are strong inferior mirages and when there are not?
Yes, I actually did a video. I think it was a live stream actually, where it was really crap conditions, where there was a whole lot of refraction, a lot more refraction than normal, and I could see further than normal, but the bridge still looked curved. So
I wasn't asking that question, but okay. So, what's your Skeptropolis? Is that your IG account?
that was my Twitter account, which I rarely look at anymore. Yeah, it's kind of old stuff.
So, do you like have a Flickr, or do you have a place where you post your images that aren't on video?
Not anymore. No.
Okay.
Most of my work is all on YouTube, my YouTube channel. I do have some Google Drive folders linked out there, but it's not everything. It's just a handful of things.
Okay, so how do we compare the image, the first image that we looked at that had the mile markers that were clear? How do we compare that one to the one that's right below it? How are those different in terms of your observation? Like, where are you?
Yeah, so the first one we looked at, I'm basically like right next to the bridge. I'm very close. There's actually like a concrete, I don't even know what to call it there, like deck. It's kind of above the riffraff right there. And so I'm very close to the edge. This second one, I've walked way down the levee. So I've walked down the levee a fair amount to take the second picture.
And it's got a different zoom because, okay, so this one we can see the
I don't think
mile marker.
I actually don't think it has a different zoom there. I think that was the
mile marker is 0.7.
No,
mile marker is 0.7, and then
there's second image is 1. You can see. Okay, so the first
right, it starts right at 1.
Yeah, the first image it starts at 0.7, and then the second
right,
image,
so like a quarter mile difference.
Well, it's just me turning the camera a little bit.
Yeah, I'm just trying to.
It's about the same zoom, though. It's got to be the same zoom because I think both of those are taken with my telescope, which is a fixed focal length.
Yeah, but you can't see the angle in the second image.
No, it's there. It's at the 1.2 mile. You can see it.
It's not. It doesn't look anything remotely the same as this one.
Well, it's because it's at a different angle. But it's there. I mean, you can see it in the image. It's just at a different angle, so yeah, it's not as obvious.
Wow. So,
what do you mean? Wow, I don't even understand why that's a problem to you. Like, that's just totally expected. Like, just how we deal with angles in everyday life. That's expected.
yeah. Okay. All right. Yeah. I mean, if you want to put any other ones that are close at hand or whatever, but I'll try to do the best I can to look back over the 3D rendering and that last image.
I could copy and paste those images if you want me to from the website that I linked last, but that website that I linked last has all the images, like every observation that I've been sharing with you guys. I have more observations, obviously, but these are some pretty good ones from a particular video, and there's actually a video linked that you can go look at from where the source footage came from.
Uh-huh.
And of course, all my YouTube videos are lower res than my actual images. My photographs are like, I don't know, very large, like 48 megapixel, I think, or something like that. Some of my photographs.
Okay. All right. I'll have to take a look at and get back to you. All right. Thanks, Sally. Appreciate it.
Have a good one, man.
don't usually get into refraction conversations, but that was very interesting to listen to.